Physics expedition number 27, studying displacement around the track. Let's take a look and figure it out.
What the damn nuggets?
Wait, what is this? Who are you?
What am I? I'm Faith Alien. I'm here because my ship crashed into some space junk. It had the initials ISS on it. I don't know what that means.
Oh my.
Oh, what? Oh, what? Why am I sticking to the ground? What is this nonsense?
You're sticking to the ground because of a thing called gravity. You see, it pulls objects toward the center of mass of a very massive object.
Really? On my home planet, what we call gravity, it just pulls things parallel to the ground. Yeah, my planet's pretty weird. So gravity is the reason why I came crashing to the ground. What else does this gravity do?
Well, gravity is what kept you in orbit around this beautiful planet. But your poor driving skills knocked you out of orbit and you were actually sucked down towards the Earth by gravity. So yes, you are in fact correct. Let me explain. Come to my website. Physics, the final frontier. Phasalian, our good pal, was orbiting the Earth in his wee little spaceship. And we want to find out the gravitational force exerted on him by the Earth. So, using our good old G, big M, little m, over r squared, we can plug in these variables to find out that force. Yo. So now, G, the gravitational constant, is that times the mass of the Earth times the mass of the spaceship all over the radius from the Earth to the ISS, because that's what he collided with. So that's how we know his radius, eh? All over that squared, so obviously that's going to be 182,638 newtons. I may be off by a few decimal points, but that's obviously the answer. Like, quick math right there. Now, second part of the question requires an eraser. It's like a smartboard. Okay, now we're gonna find the tangential velocity, because Fc, not a real force, but centripetal force is the name for it, equals mv squared over r. Now, we don't need to even do numbers yet, because we gotta solve for v, right? So, multiply by r on both sides, divide by m on both sides, and square root both sides. Okay, so v equals square root of r fc over m. Fc is the same thing as Fg, because Fg is what's making the spaceship rotate or orbit the Earth. So now, you plug in the numbers, v equals radical r is that. Fg is obviously, like we learned before, 182,638 newtons divided by the mass of the spaceship, 20,000, and that's 7,775 meters per second. That's as easy as that. Hey, Fazalian, could you help us with our physics project?
Sure, I got nothing better to do. Why not?
Okay, we need you to test out displacement by running around this track.
Okay.
5, 4, 3, 2, 1. Phase Alien, how do you feel that your displacement was 0?
What? What is this nonsense?
And to make you feel better, your average velocity was also 0.
What? What are you talking about?
It's okay, Phase Alien. I was confused too. Just come with me to my whiteboard. Why do you think Phase Alien's displacement was 0? Me too. I'll tell you why. Displacement is the distance from point A to point B when comparing your final position to your initial position. So if you go in a squiggly line from point A to point B, you have the same displacement if you just go in a straight line from point A to point B. Now, since Phase Alien was running around the track, and he started and ended at the same place, A and B are at the same point, meaning his displacement was never more than 0. Another example of this is if somebody goes walking down a number line labeled 1, 2, 3, 4, they start at 1, they go to 3, they go back to 2, they go up to 4, and then they go back to 2, their displacement is only 1, because in the grand scheme of things, they only went 1 unit from their initial starting point. So that explains displacement, but how come his average velocity was 0? Well, average velocity is equal to your displacement over time. And as we all know, 0 over anything except for 0 is 0. So that's why his average velocity was 0. Another example of this would be if Santa was flying around the world on his sleigh and he went 10,000 meters in 2 seconds, then his average velocity would be 5,000 meters per second.
So how do you guys know so much about physics anyway?
Well, we've been studying the works of our great Lord and Savior. What's that?
People, let me tell you about my best friend. He's a warm-hearted person who loved me till the end. People, let me tell you about my best friend.
You know what else is another useful friendship tool? The playground swing set. Let me teach you about simple harmonic motion.
Let's find the period of Phase Alien's pendulum-like motion on the swing. To do this, we will use the formula 2 pi times the square root of L over G. What do these variables mean? Well, L is simply going to be the length of the swing chain from the top to Phase Alien's seat, which measures 1.5 meters. And the G is gravity, which is 9.8 meters per second squared. So what do we do now? We multiply 2 pi times the square root, giving us 2 pi times 0.39, which ultimately comes out to 2.46. And of course, Phase Alien, any physics lesson would be incomplete without the inclusion of projectile motion.
Now, you may notice with projectile motion that the ball is traveling in a
parabolic arc, eh? Look, it's a parabola. Anyways, so, with that being said, that means that the ball is moving along two axes, the x and the y-axis. So, along the x-axis, the velocity is constant because no force is being applied to it, which is why Vx remains 2 meters per second. Eh? Now, along the y-axis, the ball is accelerating because of a thing we taught you about, Phase Alien, known as gravity. Ooh, yes, gravity. So gravity pulls the ball down and speeds it up. So the acceleration due to gravity equals 9.8 meters per second squared. And the height from which it was dropped was 1 meter, which is helpful in telling you how far the ball traveled horizontally. Now the reason that is because we could find out the time it takes the ball to hit the ground, and using delta x equals vx times t, we could find how far it goes, eh? So now, to find t, you gotta use good old kinematic equations, okay? So, delta y, right, equals v-o time plus 1/2 a time squared, eh? Now, there is no initial velocity on the y-axis, so cross that term out. Let's get that out of here. Hey, bye-bye. So now, delta y equals 1/2 at squared, which is, so, let's do variables. Delta y equals, a is g, because g pulls it down, equals g over 2t squared. So now, we gotta isolate t, right? So multiply by 2, divide by g on both sides. So 2 radical y over g equals t squared. So radicalize that, a. So now you plug in your variables, and 2 times 1 over 9.8 square root of that is obviously 0.45, eh? So t equals 0.45 seconds, which is an amount of time, eh?
Hey, Phase Alien. Catch.
Ow, that hurt. How strong was that throw?
That's a good question, Phase Alien. Since I threw that ball with such a powerful arm, I hit you with a certain force. Now, how do we find that force? Using a little thing known as impulse, we can find the force. All right, impulse, F delta t equals m delta v. So that means that the force exerted over a certain amount of time equals your change in momentum, or the ball's change in momentum. So, if we know everything, as in the velocity of the ball before and after, the mass of the ball, and the time of the collision, we could find the force that it hit you with, eh? Okay, so F times delta t, which is 0.2 seconds, equals 0.01 kilograms times delta v is actually 10, because before and after it switched from 5 to -5, so it was actually -10 was the delta v, so times -10, eh? Okay, so now you get 0.2f equals 0.1, and now, using our good old algebra and trigonometry, if you want, but you don't have to do that. You could divide by 0.2 on both sides, eh? And the force equals 0.5 newtons. So that's how powerful the force was, Phase Alien. Good question.
Thank you so much, Earthlings, for teaching me about these Earth physics. I've learned so much.
I guess we've transcended the need for this.
Let's go. Mother says to pick this one, and you are not it. Oh, that was such an elaborate way of picking people back in the day. Stop recording these, okay? Okay.
5, it's recording 4, 3, it's recording 2, it's recording 1, it's recording.
Yeah, I can cut it.
I know.
What? What are you talking about?
Alright, I don't know what to say now.
Alright, that's
I mean, I guess we just end that cut there.
Yeah. You're gonna be a
Wait,
shitload
just
cutting
be
in this
creepy, like,
video.
come with me to my whiteboard room.
No!
No, grab his
Come
hand.
with
No,
me.
grab his hand and do that. Come on.
It'll be funny if you come with me to whiteboard and they take you to a
No,
white
you don't have a
van.
whiteboard thing for that.
Yeah, we're gonna use. I have a whiteboard. You could just use mine.
Okay, yeah, I
Come
get.
with me to my whiteboard.
Okay. Yeah, okay, but get the shot from behind so we have an excuse for cutting. No, stay. So, okay,
We're
so
on the
I'll
other
just
side.
go like. Oh, I'm right, yeah, you're right. Okay, so from behind, and I'll just be like, it's okay, Phase Alien.
Oh, it's still recording, so yeah.
That's okay. It's okay, Phase Alien. Come
Whoops.
with me.
Do the Dora thing.
Okay. Are you recording?
Yes, I am recording. Why do my eyes look cross-eyed?
5,
Wait, what? You see yourself?
I was looking in the mirror.
3, 2, go.
Well, Faizad, that's a good question. Oh, your name's not Faizad.
I'll just pull it out from behind me.
Okay, try it, go.
If he's that's not his name. 5, 4, 3, 2, 1.
Ow, that hurt. With how much force do you throw that at me with?
You said with twice. Okay, try knocking the ball off. Alright, we're gonna try that again.
that good?
That was like angled.
Okay.
Okay, try it again. That's okay.
Oh, what the hell?
Yeah, slap a little bit harder.
Good game. Good game.